Hi everyone, I'm Bron Reichardt. I'm a PhD student at Swinburne University in Melbourne, Australia. I'm working with Deanne Fisher and the rest of the DUVET team. This is some work we've been doing mapping star formation-driven outflows in starbursting disks with DUVET. Outflows are an observational signature of star formation feedback. What we would like to know is, are these outflows primarily driven by energy or by momentum? So in energy-driven models, supernovae inject energy into the surrounding molecular cloud. In momentum-driven models, massive young stars emit high-energy photons, which exert pressure on dust grains in the surrounding ISM. Each of these models has a predicted relationship between the outflow velocity and the star formation rate surface density, which means that we can distinguish between the two models in our observed data. The reason we're asking this question is that in current feedback models, they fail by an order of magnitude in starbursting galaxies, which are the galaxies which are most likely to occur at redshifts 1 to 2. The DUVET survey is using KCWI to make resolved observations of starbursting galaxies in our local universe, which can be used as analogues to high redshift galaxies. This is an H-alpha image of our pilot target, IRSO 8. And using KCWI, we can map outflow kinematics across the entire disk of IRSO 8. And then we can compare these outflow properties to colocated galaxy properties. We have two main results. Here we have plotted the maximum outflow velocity against the star formation rate surface density for every spaxel in IRSO 8, which firstly has a signal to noise greater than 20 in the continuum, and secondly, where we've found evidence of outflows. And so our first main result is that our results are consistent with energy-driven outflows. So the dotted line here is our energy-driven model, and the dashed line shows the momentum-driven model. And you can see that our data is consistent with the energy-driven model and is not at all consistent with the momentum-driven model. This upturn at low star formation rate surface densities is caused by spaxels which are right at the edge of the galaxy. So if we exclude any spaxels beyond R90, then we see that our data is even more consistent with an energy-driven model. Similarly, we can plot the mass loading factor against the star formation rate surface density, and again we find a relationship in our data which is consistent with energy-driven outflows. Our second main result is that we find outflows across the entire disk of IRSO 8, but the bulk of the outflowing mass is not collocated with the peak of the emission line flux. So here we have H-alpha flux, phi UV flux, the H-beta flux from the narrow component, so this is from our galaxy ISM, the H-beta emission from the outflowing component, and the mass loading factor and a map of the rate of the mass which is outflowing. And as you can see, we've found outflows across the entire disk of IRSO 8. This result suggests that for observations of galaxies at redshifts 1 to 2, if we use only a single slit and focus on the peak of emission, this may mean that we're missing the strongest part of the outflow. These results also suggest that galaxies at redshifts 1 to 2 may not have the typical biconical shape of outflow, which we expect from MED2, leading to a more complex baryon cycle around starbursting disks. These results are further discussed in our upcoming paper, so keep an eye out